Welcome to the session where we are discussing the subject solid mechanics. This is the lecture number 13 and today we will start the new topic, that is constitutive relation. Now you know the probably from your elementary strength of material subject that whenever a body is subjected to forces, the body will deform, and because of this deformation the body will gets body will subjected to stresses, and that stress is directly proportional to strain within elastic limit. So that means the relation between the stress and strain is basically called the constitutive relation or constitutive equation. Now this relation, the relation between stress and strain must be linear. Okay, that means the linear elastic. And in the previous lectures we have seen that the stress at a point relates the or stress at a point consists of 6 stress components, and we have seen that the strain at a point at the same point you have the 6 strain components. And if you want to find the relation between that stress and strain, then this is called the constitutive relation. Okay, so basically here we will deal with the material behavior. Okay, material behavior. Now the equation which shows the relationship between stress and strain components is known as the constitutive equation. Now that depends on the manner in which the material resists deformation. So that means, so you have the different material for, so the relation would be different. Okay. Now the constitutive equations are mathematical descriptions of the physical phenomena based on the experimental observations and established principle. Okay. This constitutive equation describes the behavior of a material, not the behavior of a body. Therefore, the equations relate the state of states at a point to the state of state at the same point. Now, constitutive relation characterizes the physical properties of materials. Elastic solid can recover its configuration upon removal of the loading, but unloading path must be the same with the loading path. Here, so that means suppose if you have a deformation like this, then so this is the loading path. So in this direction it is stress, and along x-axis it is strain. So the loading path is this one, and if the unloading path is same, then it will be linearly elastic solid. But if the unloading path is different like this, then it will be non-linear or non-elastic limit. But under small deformations, wood, ceramic, metal, etc., shows linear elastic behavior. Okay. Now constitutive relation of uniaxial solid, and probably you know this if you do some test, that is simple tension test carried out in UTM, universal testing machine, to find stress strain curve of the specimen. The stress is found by dividing the load recorded by the area of the specimen. Okay, and strain is found measuring the change in length with the help of strain gauges. Okay, now and we will find the stress strain relation or stress strain curve for steel. If you consider the steel, then the stress strain curve, the ideal stress strain diagram for mild steel, it will be look like this. So this is your stress along y-axis, and along x-axis it is strain. So this is the stress strain, typical stress strain diagram for a mild steel. Now in this diagram, so this point is called the limit of proportionality, then elastic limit, upper yield point, lower yield point. Okay, then it goes straight, then again the stress is increases with increase in strain, and at the so this is the ultimate stress point, and after ultimate stress point the stress decreases, but if you increase the strain, and finally it breaks. Okay. So A is called the proportional limit, that means the stress strain relation is linear. So up to this limit the stress strain relation is linear, so that means this is a straight line, this is a straight line, stress strain relation is linear. Okay. Now B is the elastic limit, B is the elastic limit. So material get back original configuration upon unloading. So that the elastic limit is the limit, and within limit if you apply the load on the body, then after removal of the load the the material get back original configuration upon unloading. Okay, clear? And C D is the yield point, so C is the upper yield point and D is the lower yield point. And after elastic limit, uh, mm, if you increase the strain value, but there is a decrease in stress value, and the stress value decreases up to a point, that is your lower yield point. That means the at the point upper yield point the material starts yielding, and it continues at the point lower yield point. Then it become the strain, although if you increase the strain there is no increase in stress, so that is called basically the phenomena which is called strain hardening phenomena. This in this region it is happened, basically the strain hardening phenomena. So at this region the material becomes hard. Okay, there is no increase in stress, but after certain time the stress again increases up to ultimate stress point, then it again decreases before breaking or before fracture. So F is the failure point or the rupture occurs. So this is the stress strain diagram for a steel, or you can say the mild steel, and this is the stress strain diagram for a cast iron. Cast iron is the brittle material, this is the brittle material, and this is for aluminium. Okay, so these are the different types of stress strain curve for different material. Okay, now the steel, aluminium, etc. have elongated plastic zone, and these are ductile material. So steel, aluminium, for the steel and aluminium, so there is a elongated plastic zone, so those materials are called ductile material. Clear? So for ductile materials the plastic region is large, but cast iron or glass etc. have very less plastic zone, so these are brittle materials. Some materials don't possess specific yield point also. Clear? And brittle materials show sudden failure, ductile materials elongate sufficiently before failure. Okay, so these are the different phenomena basically, or you can differentiate ductile material and brittle material. If stress is measured based on the current area, then it is called as the true stress. And you can see from this diagram, for a steel, this is the true stress strain diagram. The true stress strain diagram up to elastic limit it is same, but from the elastic limit it deviates. The true stress strain diagram, and the engineering, this is the engineering stress strain diagram, and this is your true stress strain diagram. So these are the different. Okay, true stress is calculated on the basis of current area, then it is called the true stress. For steel, true stress continuously increases till failure. True stress continuously increases before failure. And for most materials, initial stress strain curve is linear and leading to constitutive model, that is sigma equal to C into E. Okay, so we can generalize this for most materials initial stress strain curve. So that means up to elastic limit. Up to elastic limit, the stress is directly proportional to strain, and this constant of proportionality C, and you know from your strength of material knowledge, and this C is basically your Young modulus, okay, and within elastic limit the stress is directly proportional to strain. So this is the constitutive model, sigma equal to C into epsilon. Clear? Now generalized Hooke's law, what is this? Now if you consider a cylindrical rod of diameter d subjected to tensile force P, as well as is well known from experimental observations, when P is gradually increased from 0 to some positive value, the length of the rod also increases. Clear? And based on experimental observation, it is postulated in elementary strength of materials that the axial stress sigma is proportional to the axial strain epsilon up to a limit called proportional limit. The constant of proportionality is the Young modulus, that is E. And it is also well known that when uniform rod elongates, its lateral dimensions, that means its diameter, decreases. Okay. So in elementary strength of materials, the ratio of lateral strain to longitudinal strain was termed as the Poisson ratio, that is nu. Now we can extend these informations, okay, information or knowledge, to relate the 6 rectangular components of the stress to the 6 rectangular components of the strain. So basically at a point, okay, at a particular point. So we assume that each of the 6 independent components of stress may be expressed as a linear function of the 6 components of strain and vice versa. So that means each stress component, that is sigma x, sigma y, sigma z z, sigma x is basically sigma y y, sigma z z, and tau x y, tau y x, y z, and tau z x. So all stress components can be written as a function of linear function of epsilon x x, epsilon y y, epsilon z z, epsilon x y, epsilon y x, and epsilon z x. So these are the 6 strain components, these are the 6 stress components. So they are related linearly, and that relations are known as the generalized Hooke's law. Okay, so that means we can write the stress is a linear function of strain, or the stress or this strain is a linear function of stress, vice versa. Okay, no problem. Now, so the 9 rectangular component stress are related to the 9 rectangular components of strains, and there will be 81 elastic components, and due to equality of cross shear are 6 independent components of stress and 6 independent components of strain. 81 elastic constant reduces to 36. Okay, and we will see this thing later in the future lecture. Okay. Now see, each stress component is a linear combination of strain components. So sigma x, that is C11 x epsilon xx plus C12 epsilon xx plus C13 epsilon zz, C14 gamma xy. See, so what is gamma? So gamma, you know, the gamma epsilon xx xy equal to half of gamma xy. So we can write gamma xy as 2 epsilon xy. Okay. So this is C14 gamma xy plus C15 gamma yz plus C16 gamma zx, and so this 6 strain component also related to sigma y, but their coefficients are changes. the C21, C22, C23, C24. So that means C11 up to C1 and up to C6. So you have 36. Here you have the 36 stress, that's 36 C component. Okay, so that means you have the 36 independent as independent constant, elastic constant, independent elastic constant. Okay, in general. Okay, in general. So this is your generalized Hooke's law for any material. Similarly, sigma z, tau xy, tau yx, tau zx, and these equations can be written as in matrix form also. Sigma x, sigma y, sigma z, tau xy, tau yz, tau zx, and this is the elastic constant matrix C matrix. This is your C matrix, and all the components are given, and this is the strain matrix. So how the strain is related to stress? This is your generalized Hooke's law. Okay, so we can prove the generalized Hooke's law. So we will see in the future lecture how the general Hooke's law is proved. Okay, now in general, each strain is dependent on each stress. We may write epsilon x, epsilon y, epsilon z, gamma xy, gamma yz. So this K11, K12, K3. So these are the strain elastic constant. Same thing, elastic constant. So basically, if we invert this relation, we'll get this relation. Okay. Now here we can, now we have to define, that is elasticity tensor. Elasticity tensor. The generalized Hooke's law for a material is given as sigma ij equal to Cij KL epsilon KL, where Ij KL equal to 1, 2, 3. Now where sigma ij is the second order tensor known as the stress tensor, and its individual elements are the stress components, and epsilon ij is another second order tensor known as the strain tensor, and its individual elements are the strain components. Now thisCijkl is a fourth order tensor and known as the stiff tensor, or also known as the elastic tensor, In the remaining section, we will call it as a stiffness matrix or elastic matrix, as a popularity known. The individual elements of this tensor are the stiffness coefficients for this linear stress strain relation, stiffness coefficient or elastic constant. Thus the stress and strain tensor has 3 into 3, 9 components each, and the stiffness tensor has 4 to the power 3, 81 independent elements. The independent elements are referred by the various names: elastic constant, moduli, elastic stiffness coefficient. The reduction in the number of these elastic constants can be sought with the following symmetries. Okay, so in the next lecture we will see how this 81 independent elements or elastic constants can be reduced for different material or for material symmetry. For different material it will be different. Okay, so in the next lecture we will see this thing. Okay, thank you.